All right, so welcome to this video from semiconductors. As you can see, this is the CBSE sample question paper 2022-23. This is a reasoning and assertion question. So very important question from semiconductors. As you can see, the question is, on reasoning and assertion. So let's read the question first. The assertion is that the electrical conductivity of semiconductor increases on doping. Okay. And what is the reason given? That doping always increases the number of electrons in the semiconductor. So I will quickly tell you the solution, but I will give you some explanation also. So see, what is doping? Okay. First of all, let's understand what is doping. Okay, let's understand what is doping. Doping is basically if you have a pure semiconductor, okay, a pure semiconductor such as silicon or germanium, okay, these are pure, semiconductors, silicon. Let me just correct it. If you add impurity to these, okay, if you add impurity to this, okay, impurity, these become impure semiconductors. Okay, why do we add impurity? The impurity is added because pure semiconductors, the conductivity, that is, they don't allow the current to pass through them very easily. If you want to increase their conductivity, which is electrical property, electrical conductivity, add some impure atoms. For example, you can add boron, okay, and you can add something like phosphorus, okay. What happens because of that? The semiconductor, which is the pure semiconductor, becomes a impure semiconductor. So what is the advantage? The advantage is when you add the impurity like boron and phosphorus to silicon lattice or germanium lattice, the impure semiconductor has improved electrical property. Okay, so improved electrical property, right? So let's say and this whole process is called as doping, the process of adding impurity to improve the electrical conductivity is called doping. So let's look into the question. The question is, the electrical conductivity of a semiconductor increases on doping. This is absolutely true statement. Assertion means it's a statement. I agree with this statement. Now it says doping always increases the number of electrons in semiconductor. All right. We have to find the reason why we are true. I told you we add boron and phosphorus. Now, when you do, something called as doping, which is making a pure semiconductor as a impure semiconductor, you can do doping in two ways. One, you can add a, atom like phosphorus, okay, P, or you can add another atom like boron. Okay, so you can add this too. So you have a silicon, which is pure. You can add two types of uh, impurities, phosphorus. These are just examples. There are many more examples of atoms you can add. Boron. When you add phosphorus, the electron concentration goes up. Okay, the electron concentration goes up. When you add boron, the hole concentration goes up. Holes are represented as this. Electron obviously is represented with the dark, right? So this particular approach, which is the process of, so you have two choices. One, you add an impurity which is to silicon. So this is your silicon. You can add phosphorus or boron. When you add phosphorus, electrons are extra. So the electrical conductivity of the newly created impure semiconductor. So right. So you have, for example, a phosphorus which has an extra electron. From where does the electron come? Because phosphorus has extra electron, and silicon is 4 plus, okay, 4 plus, and silicon is 4 plus, and silicon is 4 plus. This is a structure. This has an extra electron. This extra electron, the coming from the impurity like phosphorus, increases the electron concentration, the electrical conductivity goes up. Now let's talk about boron. Now boron, on the contrary, is only 3 plus. Okay, it is surrounded by silicon, which is 4 plus, silicon, which is 4 plus. This means 4 electrons in the valence band. Okay, so this is silicon 4 plus, silicon 4 plus. Okay, so this boron accepts electron from the silicon, and then a hole gets created in the semiconductor. Okay, just remember this, that boron has is acceptor. It accepts the electron, whereas phosphorus is a donor. It gives away the electron to the semiconductor. So answer to this statement, doping always increases the number of electrons in the semiconductor, is wrong. Doping always increases the number of electrons in the semiconductor, but doping can also increase the number of holes in the semiconductor. We saw the example of boron. A boron accepts the electron and creates extra holes. So boron, creates extra holes. Such type of semiconductors where extra hole is created and electrical conductivity is improved are called as P type. The other one, which are, the donor types, where electron concentration goes up, something like a phosphorus, these are known as N type. In N type, electrons go up, yes, but in the P type, the holes go up. So this statement is wrong. So my answer is, the A is true, assertion is true, but reasoning is false. So the answer to this question is C. I deliberately go in detail and explain you repeatedly so that you never forget this. It's easy for you because questions can come in many forms. They can ask you to draw, the atomic level diagram. So you know what to do now, right? It should be boron 3 plus. It should be phosphorus 5 plus, as I drew here, right? So this is one structure that I drew for N type. This is another type of structure that I drew for P type. So this is your P type, which I drew. I hope this helps. I have numerous videos on the topic of semiconductors. Please watch my playlist. No channel in the country, no application in the country, no website in the country is going to the details I'm going to and explaining you. Without explanation, you learn nothing. You only learn when you get the explanation in physics. Solution is just an addiction. You will see the solution, you will forget the solution. But if explanation is given to you in a channel like this, the reasoning will stay with you forever for your examination. You will never forget in your life. So do not forget to subscribe to this channel and wait for my next video. Thank you very much.